Hello, everyone. Uh, Today we have Dr. Shinsuke Takasao with the talk numerical modeling of flare loop-top region. He received a PhD from Kyoto University in 2016. Then he continued his research as a postdoc at Nagoya University and the National Astronomical Observatory of Japan. In 2020, he became an assistant professor of Osaka University. His PhD thesis about the numerical work on solar flares received the IAU PhD prize in 2017. So today we have this talk, and welcome. I will give you a warning 5 minutes before the end. You have 45 minutes. Please go ahead.
Okay, thank you very much for the introduction. I'm Shinsuke Takasao, and I'm very happy to give a talk here. Today, I'd like to introduce our recent numerical work on the solar flare, especially we focus on the image scale processes in the rooftop regions here. This work is done by with a collaboration with my student, Kengo Shibata. He is different from my supervisor, Kazunari Shibata. So this is so I'm very happy to introduce our work with my students. Okay, let me begin with a brief introduction of solar flare. So we have a sort of a standard model for solar flare, and this is a schematic diagram of a Mant-field structure. We have a flux slope up around here, and it is often seen as a erupting flux slope in EUV images. And the flare loops are clearly discerned in the soft X-ray images. And the energy released in the corona is transported to the lower atmosphere and heat up the chromosphere. That is seen in the H-alpha images, for example. And we see the filamentary bright structures, which is called flare ribbons, and the magnetic neutral line divides two ribbons. If we are very lucky, then we find plasma-like structures in the reconnecting regions. Now, this is all the observations that find the plasma blobs in current sheet-like structures. And then we see the bright blobs, and we interpret that the plasmoids are formed and ejected and coalescing the current sheet and ejected away from the current sheet to the sunward or the anti-sunward directions. Okay, this is a brief summary of the solar flare model. And next, I'd like to see introduce the thermal and non-thermal emissions in X-rays. Here is a soft X-ray image of the solar flare, and if we look at this region in hard X-ray, we see the bright sources in these regions. Here we see the non-thermal or super hot above the rooftop source, which is much fainter than the non-thermal footpoint sources. And this is we call this source as above the rooftop source because they often appear well above the thermal soft X-ray loop. And based on the standard model, this region may correspond to the the termination region of the reconnection jet, where the reconnection jet energy would be efficiently converted to the thermal and the particle energies. And the non-thermal electron beam will transport will penetrate to the lower atmosphere to produce the non-thermal footpoint sources via the SEC target mechanisms. And the point is that here that we have here that we expect the most important energy conversion, but that this region is much fainter in hard X-ray than the footpoint sources, which this makes observational studies of coronal sources very difficult. So this is one big reason why we don't understand the particle acceleration mechanisms in the solar corona. And nevertheless, that many numerical studies have been carried out to understand the electron acceleration process in the corona. Here, I want to briefly summarize the previous works. Previous studies investigate the electron acceleration process in these three regions: the reconnection region, of course, and the above the rooftop region and the footpoint regions. And I'd like to briefly introduce some important works. And this talk mainly discussed the rooftop region. This point, and this talk focus on the MHD scale structure of this region, and which will be the important for electron acceleration trap. And please note that this talk does not cover details of kinetic sphere processes. So, as you may know, that many studies focus on the reconnection region as a to study the acceleration processes. The high spatial resolution simulations have shown that reconnection sites are generally turbulent, and stochastic acceleration seems to work efficiently. And turbulent reconnection region can form magnetic flux slopes or plasmoids. And people have been discussing the importance of plasmoid dynamics. For example, these studies pointed out that the coalescence of plasmoid can lead to efficient electron accelerations. And now that I move to the south point of this one, this region, the footpoint regions. The footpoint region can be electron acceleration site. This idea is motivated by some observation that the coronal electron number may not be sufficient to explain the hard X-ray emissions from the footpoints. The idea is as follows: that after the reconnection occurs, the magnetic twist will be released, and the magnetic twist will be transported as an alpha wave and to the footpoints, and then the producing the strong electric field here, accelerating the electrons. So this is a type of the direct acceleration around here. And okay, the next one is the main topic, of this talk, the above the rooftop region, I will use ALT as an abbreviation for this term. Okay, this is our O2D MHD simulation of a solar flare with a single X point reconnection. So the color shows the density, and the white lines show the magnetic field. So I start the movie. I'm showing this movie to indicate how reconnection jet collides with the flare loops and stops. So this narrow structure is a reconnection jet, and it collides with the reconnected field and produce and form the many shocks in this small regions. And as a result of the energy release, we have a chromospheric evaporation and form the hot and dense flare loops. So, and in this region, this panel enlarged above the rooftop region, and in this region, the bulk kinetic energy of the reconnection jet has to be converted to thermal energy and probably to non-thermal particle energy. So the ALT region should be very, very important site for energy conversion in solar flares. And MHD simulations found multiple shocks in the above the rooftop regions, and also the simulations found complicated flow and field structures. And the people have been considered that the shocks would be a good accelerator, and with this in mind, the Kong et al. Performed a simulation that combines MHD and kinetic equations, and they found that the diffusive shock acceleration will work in the above the rooftop region if the ALT, if this region is sufficiently turbulent. I will come back to this point later. So now, so far, I have argued that the ALT region plays essential roles in energy partitioning and electron acceleration. But the ALT region would be very small and observationally difficult to find its location and resolve the structure. The reason is very simple. The flare size, let's define the flare size as L and the current sheet width as W. Then the ratio of these two would be similar to the normalized reconnection rate, which is typically within the range of the 0.01 to 0.1. So this indicates that this size, the size of the ALT region, should be much smaller than the system size. So we already know that the flare structure is generally very complicated. So it is difficult to find this location observationally. So how can we find that above the rooftop region observationally? So proposing a method to find this location is an important task for us. Okay, so I list out the many models proposed ever. So we already know many possible mechanisms for the electron accelerations, but still we cannot identify the crucial mechanisms. The reason is the main reason is that the comprehensive observations for the solar flares are very difficult. The corner part are very difficult to observe because of their low emissivities, which makes us difficult to identify the crucial mechanisms of electron acceleration trap. So, but I am aware that many people have made considerable efforts to overcome these difficulties. But still, that we have many problems to overcome. And in addition, that we do not have an established model that can describe the detailed MHD scale structure, especially the structure around above the rooftop region. We are working to reveal the MHD structure around this region. Here, I briefly summarize the impact of the MHD scale processes on particle acceleration trap. The first of all, the multi-field structures will affect of course, the magnetic reconnection physics. The recent studies pointed out that the guide field significantly affect the efficiency of the electron accelerations. And the multi-field structures at the large scale also affect the efficiency of particle trap via magnetic mirror. This panel shows an example of a magnetic mirror trap. The black line shows the magnetic field lines, and the blue lines show the trajectory of electrons. That we see that the electrons are confined in narrow regions, and this is advected to the rooftop regions. The efficiency is determined by the large scale field structure. And in addition to that, the thermal and the turbulent flow structures also have some impact. These structures will affect the preheating the plasma before particle acceleration. And these structures also affect the how and where shocks form. As I introduced before, the shocks would be the good accelerator via the diffuse shock acceleration mechanisms, and the shocks the shocks can produce the temperature anisotropy in plasma. If the plasma has a temperature anisotropy, the instability, the temperature anisotropy instability can occur to generate Whistler waves. Those waves can play a role in stochastic acceleration mechanisms. So with these points in mind, we are studying the MHD scale processes. So as I said, the observations of AOT regions are very difficult because they are much fainter than the foot point sources. But there are considerable efforts. Here I show one of the successful observations of the rooftop sources. This is coordinate observations among the EUV, the EUV hard X-ray and radio observations. And this panel shows the EUV images with the contours of the hard X-ray data. We have the hard X-ray source above the soft X-ray source, and from the radio data, they derive the electron distributions, electron energy distributions, and the middle panel shows the energetic electron energy distribution along the current sheet, and the right panel shows the estimated number density against the height. So we see the concentration of energetic electrons around the ALT region. So this observation suggests that the ALT region is likely the primary site for accelerating and/or confining non-thermal electrons. So so we see the good acceleration or the good confinement in this region. And let's look at the MHD results. So if we look at the MHD simulation, that we often find the multi-field structure that is suitable for electron confinement. So, for example, the Conway et al. Show that this kind of multi-field structure in the above the rooftop region, the weak multi-fields in the middle, and the stronger multi-field at the both ends. So this region can act a good magnetic trap. And this multi-field structure is naturally produced by a narrow reconnection jet. So the narrow jet penetrate into the reconnected field and pin down the field, a part of the multi-field, to form a concave structure. And this produces this multi-mirror plot. So, and in addition to that, we see the so energy scale flow structure in small ALT region determines the multi-field geometry and will affect the confinement of the non-thermal electrons. Okay, so I show that the even simple image simulation show the complicated flow structures in the ALT region, like this. That we have a narrow jet going downward, and we have a backflows as well. And the backflows is reflected again to the downward. We have a very complicated structure, and the observations show the turbulent motions in the rooftop regions. This observation is a spectroscopic imaging observations of a solar flare. So the gray color scale shows the non-thermal velocity around the rooftop regions. This observation suggests that the strong turbulence is produced in the rooftop regions, and the increase in the non-thermal line broadening is often seen in other solar flares. This is other examples that we have evolving flare arcade. We are looking at the flare lip from the side in this region, and we see that these points show that the non-thermal the region where the non-thermal line non-thermal velocity has is larger than the 60 km/s. And the people interpret that the non-thermal line broadening as the signature of the turbulence. And the study by Contour et al. Found that the kinetic energy of turbulent motions may be sufficient for energizing electrons. So the turbulence should not be ignored from the energetic point of view. As we see, the ALT regions would be turbulent. But what is the origin of turbulence? The turbulence may be generated in the reconnection region, current sheet regions, or the other regions. And we do not know the strength and spatial distribution of turbulence in this region. So we want to review the detailed structures. The observations also also show the other signatures for turbulence. They are called superarctic downforce, or SADs. This is an EUV movie. Maybe many of you have seen this movie once before. We have a growing flare loop here, and we see a downward dark voids, which is penetrating these bright regions. These are called SADs. SADs are descending dark finger-like plasma voids. And from the spectroscopic observations, it is known that they are less dense than the surrounding, and their speed is much lower than the typical outer speed in the corona. So their typical speed is about 100 km per second, and from this turbulent structures, people have been discussing the relation to the turbulence in the reconnecting current sheet and the rooftop regions. And recently, very nice paper has been published. This is the 3D image estimation by the Shen et al. This is a cutout of the density of the 3D image estimation of a solar flare. We have a flare loop here, and this plane shows the density at the center of the solar flare. So this is a current sheet region. We have a downward reconnection jet hitting the reconnecting field. And this region is a termination shock. And well below the termination shock, we see the finger-like flows or plumes. And this is the density profiles of this plane, highlighting this interface regions. That we see the development of the finger-like structures and creating the dark voids. And they argue that these dark voids will correspond to the SAD because their density and the thermal properties and the velocity is consistent with the observed values. And what is the origin of the turbulence? From the simulation that they found that the turbulent flows appear around the layer with a sharp density gradient. around here. So they infer that the turbulence is caused by a mixture of the Rayleigh-Taylor type instability and the Richter-Meyer-Meshkov instability, which is driven by the passage of the shock wave through the density discontinuity. Although the detailed analysis is quite difficult, the point here is that the turbulence can be locally generated in the ALT region. The local generation of the turbulence in the ALT region. This is an important point. So far I introduced that the turbulence is observed and the numerical models also show the local generation of the turbulence in the ALT regions. And here I'd like to introduce the importance of the turbulence in the ALT regions. Because I believe that the strength and distribution of turbulence change the story of the processes. Here, again, I'm showing the numerical work by the Kong et al., which combines MHD equations and Parker's transport equations. And the black line shows the trajectory of electrons, and red line shows the Mount field structures. So that after the injection of the electrons, this electron is transported again to this region and through it passes through the transition shock again because of the turbulent diffusion, and the going across this transition shock leads to the Fermi type acceleration, diffusive shock acceleration. So this study suggests that if the electrons are subject to the turbulent diffusions, we may expect a diffusive shock acceleration here. But if we do not have a turbulence, the story is quite different. So this is an MHD simulation plus the guiding under the test particle acceleration, test particle calculations based on the guiding center approximation by Kaneko-san. The yellow points show the electrons, and these are advected by the recursion jet and confined in this magnetic trap. And in this region, most of the electron does not get the huge energy. Most of the electrons get large energy when they pass through this strong field region via beta-tron acceleration. So well behind the transition shock. So the presence of turbulence and distribution of turbulence change the story in this way. Okay, so the aim of this study is that to update the picture of the ALT region based on the 2D MHD model by performing the 3D MHD simulations. So we particularly focus on the excitation mechanisms of turbulence and the spatial distribution of turbulence. So this is a numerical setting of our work. This is a very simplified model. We have an anti-parallel magnetic field, which is force free. We have a guide field around here. We have cool dense layer representing the chromosphere, and under the above the chromosphere we have a hot tenuous layer. We have a symmetric boundary here, and to avoid the complicated structures resulting from the turbulent reconnection, that we localize the resistivity in this region to induce the Pechek type reconnection. The numerical domain size is as follows. In this talk, I mainly introduce a 3D model without the heat conduction. We also performed the 3D model, 3D simulation with heat conduction, and obtain quite similar results. But the 3D model with heat conduction is a lower spatial resolution model. So here I prefer to introduce a higher spatial resolution simulation without heat conduction. Okay, so this is a movie that shows the general evolution of our simulation. The color shows the density, and the lines show the projected field lines. The reconnection is taking place here and forming the reconnected loops. This is an enlarged movie of the above the rooftop region. So we see the complicated structure here. So this image shows the 3D multi-field structures under the gas pressure in the XY plane. In this simulation, the y-axis shows the particle direction. So this high pressure region represents the above the rooftop region. This narrow region is a reconnection jet, and we see the tangled multi-field lines in the above the rooftop region, which suggests the generation of turbulence. And we also see some enhancement of the sharp enhancement in the gas pressure, which indicate the multiple shocks. So the above the rooftop region would be the as I will show later, the above the rooftop region is filled with the shocks and the turbulence. These panels show the development of turbulence in the ALT region. The color shows the plasma vapor. This is an image just after the formation of the fluid. The narrow jet is impinging the ALT region, and we still see the coherent structure. But as time goes by, we see the filamentary structures surrounding the lower end of the reconnection jet, and this the turbulent regions extends as time goes by, like this. So the ALT region, again, the ALT region is filled with turbulent flows. And if we look carefully at the movie, we see that the ALT region is oscillating back and forth in this horizontal direction. And this type of oscillation has been found in previous MSD model. I'd like to introduce our old work based on the symmetric 2D model. Yeah. So this is is a snapshot of the density. We have a reconstruction jet, and we have a backflow here. And this is a schematic diagram of this time. So we have a jet and backflow, and this backflow pushes away the magnetic field in this way, in this direction. And this backflow increased the magnetic pressure around here. And
you have 5 more minutes.
Oh, really? Okay. Thank you. And then we have this region is pushed back by magnetic pressure. So this region is shaking by magnetic tuning fork. So please remember that the ALT oscillation is an oscillation caused by the backflow, and our 3D model shows that asymmetric ALT oscillation can occur in 3D even in the presence of turbulence. And the observation suggests the presence of ALT oscillation. So that this is an observation done by the Reeves et al. And we have this FLIR shows a bit complicated FLIR loop structure. The expected top-down view would be like this. The FLIR loops would be something like this. And the ALT observation, ALT oscillation is observed in these regions. That these loops correspond to this region. And they performed the iris spectroscopic observation and found that the oscillations in Doppler velocity and the symmetric ALT oscillation will not be able to produce that signal. So the ALT oscillation should be asymmetric, as the 3D model indicates. Okay, so the spatial distribution of turbulence is like this. The jet is surrounded by the turbulent flows. And if we plot the turbulent energy density divided by the coherent magnetic field energy, the structure is something like this. That we see the strong turbulence in the strong turbulence is localized in the magnetic tuning fork arms. These two regions. And as shown in this simulation, the strength of turbulence is highly inhomogeneous. So the weak turbulence just behind the termination shock. And I guess that this may have some negative effect for DSA, because in this model the turbulence is sufficiently strong to allow the electrons to come back to this region. But this region may not be as turbulent as assumed in the model. So we need more considerations to think about the DSA processes. And a short summary of the ALT structure is like this. This images is taken from the Shen et al. They discussed the Levy-Taylor type instability here. So they basically investigate the local generation patterns around the lower end of the jet. But in addition to this study, that we found that the multiple termination shocks can be formed in these regions, and the local generation of patterns. As they found, we see this region become turbulent, and we also found that these two arms of the magnetic tuning fork becomes very turbulent. And we also found the ALT oscillations. So what is the origin of turbulence? I may need sorry, 5 more minutes. I'd like to discuss the origin of turbulence. Here, we see the strong turbulence in the multi-tuning programs. So to understand the origin, that we look at the gas pressure here, and we found that these regions, in these regions, the high pressure gas is confined by a curved mass field, which is called the bad curvature regions. So we have 3 or 4 bad curvature regions here, where the so-called pressure-driven instability may grow. We consider that this instability is an important source for the turbulence. So that because the time is limited, that I need to skip this slide. The pressure-driven instability is an interchange mode instability. If the plasma is confined by the toroidal field, it becomes it can easily become like this. And this region, this structure is quite similar to the region here. The high gas pressure region is confined by the curved field. And if we take the slice in this region and look at the time evolution, that we do see the development of the finger-like structures in these 2 regions. So that we indeed find the finger-like structures appear around the bad curvature regions in the ALT regions. And another important point is that the instability grows faster in the arms than the region here. The reason would be related to the formula of the growth rate. The growth rate of the growth rate of the ballooning mode or pressure-driven instability is written like this. So basically the growth time scale is the sound crossing time. And we also have an asymmetric ALT oscillation, and the turbulence structure becomes very asymmetric. And we have a turbulent, we have the compressional motion induced by the ALT oscillation that increases the pressure gradient in one arm in this region, and that enhances the growth rate, and then promote the turbulent generation. This is the scenario of the asymmetric turbulence structures. We derived we evaluate the time scales, and I will skip the most of the parts, but the point is that the growth time scale compared to the Alban time scale of the system would be much smaller than unity, which means that the turbulence can grow instantaneously in flares. Okay, so in the last moment, I'd like to show some implications for observations. We often see the oscillation in flares. They are called QPPs or QPF, the cross-phase propagating part energy waves, and we often see these kinds of oscillations in many flares. And is there a common origin in some events? Which would be the natural question. And our estimation suggests that they may have a common origin. This right panel shows the line difference of the density. You see that some waves are propagating waves are generated from the rooftop region. So if the ALT region is a very good important site for the electron acceleration, then the ALT oscillation may account for both the QPP and the QPF in some flares. And the MHD models suggest that the locally oscillating regions would be the ALT region. So that the oscillating Doppler shift will be a good indicator of locations of ALT regions. So that I'd like to suggest that the combinations of spectroscopic observations and X-ray and radio observation will uncover rooftop processes. Okay, so that I think that I need to stop here.
Okay, thank you very much, Takasawa-san. We are open for questions, so please raise your hands or unmute your microphone and ask question or make a comment. I do not see any raised hand yet.
I don't know how to raise my hand, but I could ask a question, of course.
Please go ahead here. Yeah.
Okay, thank you. Thank you. Thank you, Takasawa-san. That was a very, very clear presentation and very interesting physics of the reconnection jet. But the question is about how intuitive you feel about the localization of the flare energy into this very narrow feature when the energy storage is presumably very diffuse originally in a large scale volume of the corona. How does it all get into the jet, and do the simulations show the propagation of energy from the large scale to the small scale in such a focused way?
So do you mean that the large amount of the energy can be transported by, for example, the waves away
I'm asking,
outside the different object?
Yeah, I'm asking if you can track the energy through the simulations that produces this focusing effect.
Yeah, we measure the in our model that we measure the kinetic energy of the reconstruction jet, and that is similar to the released magnetic energy. But in our model, in the large domain, the magnetic field is anti-parallel, so the weak guide field. So if the magnetic field has a large guide field, then I guess that the large amount of the energy will be transported into the transported to the lower atmosphere in the form of the waves, like alpha waves. So that would be that should be investigated as well.
Okay, thank you.
Thank you.
Okay, Judy, please go ahead.
Sure. Thank you very much, Takasawa-san. They're very, very nice simulations and very interesting physical explanation. I was wondering whether you're assuming uniform anomalous resistivity in the third direction, into the plane.
Right.
Because that,
yeah, we assume.
if most of the time we think that there's probably patchy reconnection in the current sheet, and so that would even add to the likelihood of some sort of turbulence, because you have another dimension of changes. What kind of Lundquist number were these simulations?
That it's because our resistivity is localized in this region, that it's difficult to show the Lundquist number. But
what about in the rest of the simulation, the rest of the system?
Sorry, that I haven't estimate the numerical Lundquist numerical resistivity in our simulation.
Yeah, the reason I'm asking is just that when you form a current sheet, of course, if you form it in a different way, through inflows, usually the current, if you get above 10 to the 4 or something like that, you'll get plasmoids.
Right.
That will, of course, give you a different kind of inhomogeneity in the system. In this system, yes. I don't think you have the possibility of forming plasmoids because it's a purely Pechek configuration.
Right. I'm aware of that the turbulence can be generated in the reconnection region and the current sheet layers. And the point of my talk is that the turbulence can be generated locally without the injection of the turbulent flows.
Yeah,
So
no,
that-
very interesting. Thank you.
Yeah, the time scale and
That 400-second something.
right. So that the growth time scales can be much shorter than the system evolution time scale. We can assume that the ALT region is always turbulent
Mhm.
if we have a sufficiently strong backflow in this region.
Thank you.
Okay, Jim, go ahead.
Hi there. Very much enjoyed your talk.
Thank you.
I think you've made a very convincing case that this alt region becomes turbulent. But my question has to do with the amount of energy that could be associated with that turbulence, because in the end, of course, we're trying to figure out, what's the dominant region where the particles are accelerated. And it seems like one of the mechanisms you propose is a bad curvature instability driven by the high pressure that's within this cavity region. But if there's a high pressure region in the cavity region, that means that the conversion to plasma energy has already taken place. And so I'm wondering how much energy is really available in this turbulence to actually heat the plasma beyond what happened when the reconnection occurred, for example, in the Petchek-like shocks that you probably have in your simulation.
Yeah, that's a very good, important point. Yeah. In this model, as you mentioned, that we assume that the plasma is efficiently thermalized here. So yeah, I can't give a number to you, but yeah, I will investigate the point in future.
Great, because I think, that's one of the things one needs to discuss in terms of trying to figure out the role of turbulence versus more coherent processes. The total energy content does make a difference, right?
Right.
A follow-up question on this plot. This has been, so is the color bar showing the level of the turbulence? Is this like 10 times the b squared, the highest one?
Right. Compared to the coherent component of the energy.
So if that's the case, there's a lot of energy, right, Jim?
The plasma beta along here is about unity. So that.
Yeah, but this is, of course, a very low field region, right?
Okay.
Right, exactly that.
Okay, other questions or comments? In particular, I propose those who attempt to use chat, just go ahead and ask question, because no one is reading at the moment what is written in the chat. Yeah, David, go ahead. No?
Sorry, yes, thanks, Gregory. I just can you hear me?
Very bad quality.
Okay, let me try to adjust settings.
It's now it's fine. I think you can go ahead and ask.
Okay, yeah. So basically, yeah, I had very three brief points. Basically, I was a bit puzzled with third order accuracy in space and time. I mean, usually, if you use centered finite differences, it's usually seconds, fourth, or sixth order, or even order. That was a bit puzzling. So, I mean, it's 2 points forward and 1 point backward. This is a bit puzzling. Okay, the second comment was the actually, I think the premise of turbulence or not, I think this point was a bit overplayed in this talk, because when you actually consider kinetic effects, the meandering motion of electrons always yields chaotic electron trajectories. So I think this is a bit, when you switch on and off turbulence, I think this point was a bit overplayed. And if I may, I would like to, there was this question raised by Judy already that about anomalous resistivity. And particularly in these plasmoid induced reconnection models, this is quite important, because I remember Magara et al. 1997 models, when they used specific models for anomalous resistivity, where not all plasmoids would actually raise upwards for particular magnetic scale heights. So I think this issue of anomalous resistivity models is of concern. This is all I wanted to say. Thanks.
Okay, would you like to respond to anything?
Okay, so the first about the first point, the third order accuracy in space and time, mean that we this is accuracy for the spatial reconstruction under the time integration order. So we use Runge-Kutta, third order Runge-Kutta time integrations and the third order PPM spatial reconstruction. And about the point two, about the turbulence, now that we perform this image simulations, and we cannot discuss the kinetic scale physics only from the MHD model. But here I implicitly assume that the turbulent can produce the kinetic scale waves, and which may affect the stochastic acceleration processes, and also that they change in the fluctuating field, the mud field strength along the field line drastically changes, which may affect the trapping in the region, in the electrons. And about third point of the about the anomalous resistivity, I'm aware that our recognition model is very simplified, but we put the localized resistivity to produce a simple recognition jet. We do not have a plasmoid under and we do not have the CME and we assume the symmetric boundary here, so that we may have a CME like ejection probably here.
Okay, so thank you very much again. Our time is over. People are leaving, so let me thank you again, and welcome everyone at our next event in a month.
Yeah, thank you very much.